right, we're going to take a look at this last piece to our binomial probability. And what we really want to do is we want to connect together this discrete probability, these discrete situations, okay, where we have these finite amounts of things that can happen, making these rectangles here and those rectangular probabilities. We want to compare that to the continuous situation where you have infinite many possibilities. You can have 2.667 things or whatever. All right, so we want to see, how do those probabilities compare? And when do they get really close to each other that it doesn't really matter if we compute one way or the other? Okay, because we might find we like doing the normal model approximation a whole lot better than that binomial approximation. And so we can just go with that. All right, so that's why this is an important thing to look at. So first, when we looked at that binomial part of our formula chart, see here when we looked at this thing that I've written all over here, and we take a look at this middle piece where we've got the binomial section, then we also see, of course, that we have got this mean, this expected number that you would have out of a set number of items, and then that standard deviation, okay? So I think that this mean makes sense because if you have, 20% chance of something happening and your n is 100, I think naturally you see that's 100 times 0.2. You're going to expect about 20 of those items to occur. All right, so those formulas kind of make sense when we take a look at them. But let's go ahead and go through that. So here, suppose that we have the probability of having a boy or a girl is equally likely at 50%. We'll examine the next 10 babies born. So out of 10 again. So we're going to determine some probabilities based on that information. So we're going to do that binomial of getting exactly 7, 8, or 9 babies born amongst those 10. So I want you to take a moment, go ahead and do that. Compute this probability here of 7 or 8 or 9 amongst the 10. So you'll be doing those three binomial situations separately and then adding those three pieces together. Okay, so I want you to do that. I'm going to take a look at what that looks like on this normal model picture here. So you go ahead and compute while I tabulate that here. All right, so you can see we had that 10 choose 7.5 to the 7. Oh, you know what? I forgot to put a little exponent here I have missing. So I'll go back and fill that in. So what exponent goes there? Let's kind of talk about that. What goes right there? Because we know that this number, this exponent plus the failure should total to the total n. So what do I have missing here? Of course, I've got a 3 missing. If we have 8 successes, what do I have missing here? How many failures? There's 2. If I have 9 successes, then I've got 1 failure. So I had those exponents missing. So I'll go back there and I'll fix that. But here we have that comes out to, when we compute that with our calculator, the PDF of 7 plus the PDF of 8 plus the PDF of 9 at 17.09% chance. And look at what that came out here. Look here, 17.09%. Okay? Now, interestingly enough, if we did, let's see if I'm going to do that. Oh, now I'm going to get that average number of boys that we expect to be born among those 10. So we're going to use this formula from here. Out of 10, 50% chance of boys, how many do you expect to be born? 10 times 0.5, so 5. And then you can compute this and get that standard deviation. So here is what that mean and standard deviation is. So the 5 baby boys, and with a standard deviation of 1.58. Now, take a look at this here. This is what these three rectangles is what I just computed and got that 17.09. Well, technically, see, this is interesting, and I'm kind of learning this too. From here, technically, that's if we go from 6.5 to 9.5, that's what's giving us that close approximation of the closest to the normal. Interesting. Um, hmm. But what I can see us doing is say, okay, we've got a mean of 5, a standard deviation of 1.58. Let's get our two z-scores from 7 up to 9 and compute this area from 7 up to 9. And look at that. That's 9.63%. Interesting. So see, if we were to look at a picture of that on here, what does that actually look like on this picture? Well, that's just going from here up to the 9. So you can see it kind of looks like less area than what is in those rectangles. Okay? So it's interesting that, of course, going from 7 to 9 on the normal model is really, a little bit farther away than we would have hoped and expected it to be. Here, when it computed it from 6.5 to 9.5, it's actually a fairly good approximation. So that makes me curious. What's the rules? Why are we going from 6.5 to 9.5? So I'm gonna investigate that. So it's very interesting to take a look at that and see what's happening. Now, I can tell you, so we're a little bit off, but I can tell you one thing that, why is this happening? Well, it's because we have these discrete, finite rectangles, 7, 8, and 9, that are much different than this curved normal model area. Okay? Plus, according to this, the curved area is closer if we go from 6.5 to 9.5 instead of from 7 to 9. So interesting how that falls out. I will tell you that and watch this. This is very interesting. As your um, N gets bigger and bigger, look at how these rectangles get a closer approximation to the normal model. Okay, and so then we can go ahead and compute those areas there, and they get even closer tabulation than for the binomial to the normal. See in here, you can see there's not much discrepancy. And look at there, look at that selected area. They are 100% away from each other. Okay, so very interesting relationship between the binomial and the normal, and I really love how you can kind of play with this. On your Canvas page, there are these two sites that you can go to. This other one is GeoGebra, and it's also very, very interesting because you've got the binomial approximation. You've got certain size samples and then certain size probabilities that you can play with and explore. And then you've also got these things here where you can see the relationship between what is, see, look at here. Whenever I do my binomial, it goes all the way out to 13. But if I go my normal all the way out to 13.5, that's a better representation. So interesting to compare that and to see when are these areas actually really pretty close. See, look at there, going out to 13, but then 13.5 on my normal approximation. So all right, definitely worth exploring if that interests you, that relationship between those. But for now, that's all you get. And actually, your reflection that you are going to do is going to ask you, about that connection between that binomial and that normal model. So you're going to explain in your own words why there is that discrepancy. Why do you think that's happening between that binomial approximation and that normal model approximation? And go and explore those two sites to see what you think is actually happening. Very interesting. Come and tell me some things about it because I want to see what's really happening here. All right. Good luck to you on your assignment then, and hope that you understand how to do your binomial probabilities and the approximation of them normally.